Hi, I'm Kirk Weiler, and today we're going to be talking about differentiability in Math 4 Honors. The term differentiability and the term differentiable are new terms to you, probably. All it means for a function to be differentiable at a particular value of x is that the derivative exists there, that you can literally draw a tangent line and quantify its slope with a finite number. Did you catch that? Finite number. So all it means for a function to be differentiable at x equals a is that f prime of a exists. Oh yeah, that's right down there. Alright, that's all it means. Alright, it's got to exist, it's got to be finite. Now, the vast majority of places on a smooth function, the derivative exists. But there are particular reasons why the derivative would fail to exist. And there's three primary reasons. I'm just going to state them outright, and then we're going to look at each one of them in turn and understand why it causes a derivative to not exist. So, one reason is simply that the function is not continuous at the particular value of x. That should make some sense, even if we don't know how it's going to pan out. The function not being continuous there seems like it should be important. The function has a corner at x equals a. Notice that corner is in quotes because we really haven't defined what a corner is. And finally, f of x has a vertical tangent line at x equals a. This might be the one that makes the most sense to people, because if you have a vertical tangent line at a particular x value, then its slope wouldn't exist, and therefore the derivative wouldn't exist. But all in good time. Let's take a look at why a discontinuity can become so problematic for the derivative. Now, to do this, let me make sure that that's completely in my view screen. To do this problem, what I'd like to do is I'd like to sketch this function. Pause the video for a minute and sketch this piecewise function. Alright, let's take a look and do it together. Alright, what I should know immediately about this piecewise function is that it's piecewise linear. Alright, and again, depending on how you learned how to draw it, I know the cutoff point is at 1. What I tell my students to do is to literally take the first curve and kind of sketch it in dashed. So this is y equals x plus 1, and y equals x plus 3. Same slope of 1, but a y-intercept of 3. And now I have them fill it in. So for instance, I know that f of x applies at x plus 1 for x less than or equal to 1. So what that means is it's going to look like this. And for x greater than 1, we would have that open circle, and it would look something like this. So we clearly have a discontinuity at x equals 1. A location where we raise our pen up and it skips along. Now remember, if we were to use the limit definition of the derivative, right, what we would do is we'd put a value of x here, right, and then we'd pin our value of x here, and we would draw in that secant line. Sorry about all the lines here. And we'd say, well, we have f of x minus f of 1, all divided by x minus 1, and then we'd look at the limit of that as x goes to 1. But hopefully you can see what the problem is here. As I allow this x-coordinate to get closer and closer to 1, right, then the y-coordinate is doing more and more like this, and in fact what's happening in this discontinuity is that that line that's connecting the two is getting closer and closer to vertical. And in fact, if we allow x to approach from the right, if we allow x to approach 1 from the right, as we have it drawn in the picture, the top is not approaching 0. Remember, the derivative ultimately is the change in y divided by the change in x as delta x goes to 0. But almost always, when delta x goes to 0, when the run goes to 0, so does the rise, right? So in almost every situation, when the run goes to 0, the rise goes to 0. But in this case, right, the rise would actually be going to 2 while the run was going to 0. And we just can't have a slope that way. we could look at every type of discontinuity that exists, not particular to this particular function, but I mean, can you imagine kind of a classic discontinuity, a hole, right? Say you had this, right, at x equals a. Well, now it's going to be a very large problem if I try to find the derivative at a, because I can't even do this, f of x minus f of a over x minus a. I can't even look at this limit. If I do, right, this thing isn't even defined. So anytime I have a discontinuity, at any x value where there's a discontinuity of any type, a hole, a jump, a vertical asymptote, any discontinuity is going to mean I do not have a derivative there. All right, let's take a look at corners. Corners are pretty awesome. All right, and the classic function that has a corner is the absolute value of f. Pause the video for a moment and sketch the graph of f. If you think you can do it, continue on and also sketch the graph of f prime, but if you can't, hold up and I'll show you how to think about that. Pause the video now. Okay, let's take a look. So, pretty easy, right? Don't get me wrong, not easy for me to draw a completely vertical y-axis, but the viewers of my video are very forgiving. So here's f of x equals the absolute value of x. Now, let's take a look at f prime of x. Never forget that the y-coordinates on f prime, right, in fact, I'm going to label the y-axis as f prime. The y-coordinates on f prime for any given x should be the slopes. So if I went over here to, let's say, -1, I would know that the slope right here is -1. And if I went over here to -2, I would know the slope here is -1. In fact, the slope anywhere along this portion of the curve, the slope is -1. Also, the slope anywhere along this side of the curve is +1. So the derivative graph would have to look something like this. It would have to be a constant, -1. That doesn't look very constant, but please excuse me. And then a constant 1. Now, of course, there's a problem here. Because the way I've drawn the graph, f prime is not a function. It's not a function because it violates the vertical line test right at x equals 0, right? At x equals 0, where our corner occurs, at x equals 0, right, what slope do we have? Do we have -1? Do we have +1? And the answer is we don't have either. What we need to do is we need to put an open circle there. And you can explain this in a lot of different ways. One way to explain it is that the derivative can only have a single value at an x value. Only one value. It can't have 1, it can't have -1, and you can't just arbitrarily pick. Another way to say it is you could say there's an infinite number of tangent lines, right? For instance, you could have a horizontal tangent line there, but you could also have tangent lines that are non-horizontal, right? Interestingly enough, every one of these slopes would be between 1 and -1, which kind of makes sense because that's sort of what this graph is indicating. That somehow we're immediately going from a slope of -1 up to a slope of +1. And therein lies the definition of a corner. If the slope instantaneously changes, instantaneously jumps at a particular x value, right, not continuously and smoothly changes, but instantaneously jumps, then we get a corner. The technical way of saying this is that the right-hand derivative and the left-hand derivative don't match up, meaning that as I approach x equals 0 from the right, my slope is 1. As I approach x equals 0 from the left, my slope is -1. And this happens all the time. Let me kind of sketch a different looking curve really quick. You know, corners can come in all sorts of different varieties. Some are even given special names like cusp. You could have something like this, right? Where, you know, I'm coming in and I've got like a slope that, I don't know, maybe the slope coming in at this point is, let's say 1. but coming in from this direction, that's not good. The slope maybe is -2. Please excuse the bell there. So we have this sudden change in slope, and therefore we have a corner. We don't even have to have a sudden change going from positive to negative. We could have a nice positive slope and then another positive slope. So maybe this thing has a slope of 2, but it immediately transitions into a slope of only 1. And those abrupt changes in slope are what give us corners. They're very often introduced by absolute value functions. I'm going to pause the video just for a second, okay? Alright, let's get back to it. So we've already seen 2 ways that a function can fail to have a derivative. 1 is if the function is not continuous there. 2, if the function has a corner, a sudden change in the value of the slope. The last one is the one that I mentioned is most intuitive to people, but probably the hardest to spot. It's fairly easy if you're looking at a graph to see a corner or to see a discontinuity. On the other hand, a vertical tangent line is a little bit trickier. So what we're going to do is we're going to look at a very important function, the cubed root of x. And what we're going to do is we're going to sketch the graph of f, and we're going to find a formula for f prime. And then we're going to think about where f prime fails to exist. Alright, now, hopefully you know what the graph of f of x equals x, the cubed root of x, looks like. But keep in mind, even if you don't, it's the inverse of x cubed, so you should be able to produce it. Pause the video now and see if you remember what the cubed root of x graph looks like. Alright, let's take a look. So, the cubed root of x, let's see if I've got my pen here. Uh-oh. Somehow I opened up Windows Live Movie Maker. No offense, but I'm not doing that right now. So, the cubed root of x looks something as follows. Looks a lot like x cubed, but then goes something like that. So this is y equals the cubed root of x. You probably already know where it's going to have a vertical tangent line, but let's see that when we do the derivative. So pause the video for a second, find the derivative of y, and then simplify it. Alright, let's take a look. We can find the derivative by simply applying the power law to x to the 1/3. So dy dx, we're going to bring our 1/3 down, so to speak. We're going to drop our power by 1, and we're going to get 1/3 x to the -2/3. I'm going to write that back in terms of a fraction with a positive exponent, and then I'm going to write that again in terms of the cubed root of x squared. I'm not sure which is easier for you to think about, this quantity or this quantity, whichever way makes it helpful for you. But regardless, one thing that I always want you to remember about slope is that it is rise divided by run, right? Divided by run. Let's try that again, get rid of it. Rise divided by run. And with a vertical tangent line, what we know is that the run must be equal to 0. And the only way that 3 times the cubed root of x squared will be equal to 0 is if x is equal to 0. Alright, so we have a vertical tangent line. We have a vertical tangent line there. You can see that. I'm going to change my color to red. Alright. Not the easiest one to see, and unfortunately I didn't do the best job of drawing either my tangent line or my cubed root graph, but we do have a vertical there. One way to also think about it is the graph of y equals x cubed, not the cubed root, but x cubed has a horizontal tangent line at x equals 0. I want you to be careful. Just because the denominator goes to 0 in a derivative doesn't mean you have a vertical tangent line, because you could actually have a situation where the graph doesn't even exist, right? A good example of that would be something like, let me change back to black. If I had something like y equals 1 over x, so this is a little sidebar. I do this a lot on my students. If I have y equals 1 over x, y prime is negative 1 over x squared. So if all you knew was this, you might think that this graph has a vertical tangent line also at x equals 0. The problem is it doesn't have a vertical tangent line there because the function doesn't even exist there, right? I can't say that it's got a vertical tangent. It does appear to be heading towards vertical, and that's giving me a vertical asymptote. But what I can't say is that it actually has a vertical tangent line there because the function doesn't even exist. Hard to draw a tangent line to a function that doesn't exist. All right, let's take a look at sort of the culmination of this. The idea of differentiability is that it gives us functions that are smooth functions. This is kind of cool. So what we're going to do now is we're going to take a piecewise function, and we've done this before, and we're going to look at some mysterious constants, in this case h and k. And we're going to try to figure out what values of h and k will make this piecewise function continuous, and what values of h and k will make this function differentiable at x equals 0. Now, let's take a look in letter A. It says what values of h and k will make it continuous at 0. Now, for continuity, remember what you know is we would know that the limit of g of x as x goes to 0 would have to be g of 0. That's the definition of continuity. Now, g of 0, that's actually pretty easy because it's defined just by that square root function. Square root of 0 plus 1 is 1. Now, that also happens to be the limit of g of x as x goes to 0 from the right. So all we have to do is make sure that the limit of g of x as we come into x equals 0 from the left also equals 1. Well, that's just going to be 0 minus h quantity squared plus k, right? That's the limit coming from the left. That has to be 1. Negative h quantity squared, negative h times negative h, is positive h squared plus k. That's actually our answer. What in the world does that answer mean? What it means is that if I pick any two values of h and k, any two, and I square h, and I add k, right, and I get 1, then this function is continuous. For example, let's say that h was 2, right? If k was negative 3, this equation would be satisfied, right? I'd have h squared, which would be 4, plus negative 3, and I'd get 1. I could do this for quite a few different values. I could say, let's say that h was 1. K would then have to be 0, right? Because 1 squared would be 1, plus 0 would be 1. So there are lots and lots of values of h and k. As long as they satisfy that equation that's in the box, there's lots of values of h and k that will cause this function to be continuous. Letter B then says, find all values of h and k that make the two derivatives equal at x equals 0. And it asks why that doesn't guarantee that the function will be differentiable there. So let's take a look at this. This is going to be a little bit more tricky because it's going to actually involve us doing some work and finding a piecewise derivative. Alright, so what I'm going to do is I'm just going to take the derivative of both the upper, or the first formula, and the derivative of the second. Now, I don't have the actual equation on my screen, so I'm going to try to pan back up a little bit so that we can maybe see that as we're working on this problem. Is it going to fit? Oh, just barely. Just barely. Hopefully you can see that. So when I take the derivative of x minus h squared plus k, keep in mind h is a constant, k is a constant. I'll take the derivative of x minus h squared. I'll do that with the chain rule. I'll bring the 2 down, multiply it by x minus h. I'll raise that to the first. I'm not going to write the first power because I don't want you to think it's a prime. Then I'll multiply it by the derivative of the inner function, which is 1. Now I have to add to it the derivative of k, but k is a constant, so its derivative is 0. I think I'm going to just rewrite this as 2 times x minus h. I'm going to leave it like that, though. You could distribute the 2. And I'm going to say that's for x is less than 0. Now I'm going to also take the derivative of root x plus 1. I would have to do that sort of using the chain rule as well, but hopefully I've memorized what the derivative of the square root graph is. It's going to be 1 over 2 times the square root of whatever. I would then have to go on and multiply it by the derivative of the inner function, but that's the derivative of x plus 1, which is also 1, so we're just going to get this. Now, I'm going to actually just say x is greater than 0. I'm going to leave off the equality, because quite frankly, for the derivative to exist at x equals 0, these two quantities have to be equal at x equals 0. So, I'm going to substitute in x equals 0. Alright, I'll get negative 2 times h equals 1/2. And h will equal negative 1/4. And again, this takes a little bit of interpretation. Alright, last time we had like these two things, h and k. This time the k went away because we took the derivative and it was a constant. How do we interpret this? The way we interpret this is that any values of h and k, where h is negative 1/4, and k can be anything you want it to be, will make the slopes match up. So if h equals negative 1/4 and let's say k equals 3, then the slopes will meet up. So this is one possibility. Just one. There's an infinite number of them because k can be anything it wants to be as long as h is negative 1/2, and that makes the slopes match up. Now here's the $64,000 question. Just because the slopes match up, it doesn't guarantee that the function will be differentiable there. It does guarantee we won't have a corner, but it doesn't guarantee that it'll be differentiable there. And why is that? Think about the three conditions of differentiability. Why am I not guaranteed, once I have the slope from the left, that's going to be this guy, slope from the left, equal to the slope from the right, why won't I necessarily have a derivative there? Pause the video now and actually think about this a little bit if you need to. Alright. The reason that it may not be differentiable, the reason that it's actually not likely to be differentiable, is because to be differentiable, yeah, the slopes have to match, and that's going to happen as long as h is negative 1/4, right? That will avoid a corner, no corner. On the other hand, we also have to have a continuous function, but that's only guaranteed by this condition. So in fact, in order to have the derivative exist, we have two conditions. One condition, which really is a condition on the function itself, and another condition generated by the derivative. You know what this is? This is two equations, two unknowns. This is a system, right? So one equation, h squared plus k equals 1, guarantees no discontinuities. On the other hand, h equals negative 1/4 guarantees no corners. We don't have to worry about the vertical tangent line in this situation. When I put the two together, then I guarantee no discontinuities, no corners, and differentiability. Now, many times the no corner condition would involve, let's say, two quantities. Here it only involves one, so it's really rather easy. All I have to do is take negative 1/4, I guess the slowest way imaginable, I have to substitute it in there. So I have negative 1/4 squared plus k equals 1. That's going to be 1/16 plus k equals 1. And that tells me that k is 15/16. So when k is 15/16 and h is negative 1/4, we're going to have a smooth function, a smooth, continuous, differentiable function. I'm going to actually try to graph this for you. I'm going to try to put it in the graphing calculator and see if that works. Alright, we'll see how well this works. Excuse this and my children. Alright, I'm going to put this into my calculator and take a look. Why not? I've got a graphing calculator on my computer. I'm using the TI-84 Plus. You might be using something else. Let me get the graphing calculator into view. I'll register later. Whoever registers right now. So here's my graphing calculator. I'm going to go into my y equals command. I'm actually going to sort of put the function in, but I got to put it in the two pieces. So what I'm going to do is I'm going to put in x minus h. Now remember, h was negative 1/4, so I'm going to put x plus 1/4, and I'm going to square it, and then I'm going to do plus k. What was our k? Our k was 15/16. Now there is a way to graph piecewise functions on your calculator, but I'm not going to get into that in this lesson. I'm then going to put in, whoops, let's try that again. I'm then going to put in square root function of x plus 1. Now really what I very much care about is I care about what this looks like right around x equals 0. But why don't we do a standard zoom and see what happens? We'll do zoom option 6. Alright. I'm going to just turn off some things here. Right here, let's zoom in. Zoom in our window. I like zoom box. It's a very, very nice option. It allows me to draw a box around an area that I'm interested in. I hope that you've seen zoom box before. Opening up a box right around where one of those things sort of leaves off and the other one begins. So what's happening, I'm not sure I convinced you very well on that, is that the quadratic is coming down, and right at x equals 0, the root is taking off, but in a smooth way. There is a way to actually do this without, or by putting parentheses in. I do tend to show my students this. It's a little bit tricky, especially when you're dealing with it on a computer instead of a graphing calculator. If you can follow along, this is kind of neat. You enclose the entire function in parentheses, and then you multiply it, now I'm going to go down here, by its domain interval. That probably doesn't make a lot of sense, but meanwhile the graph is changing as it moves along. If you're watching this and you're in my class, don't worry, you'll learn it soon. It's a really rather neat technique for graphing piecewise functions. It's very sly. So this formula only applies when x is less than 0. This formula only applies when x is greater than 0. Alright, and there we have it. The quadratic is coming down, and it's transitioning smoothly into the root curve. Don't worry about that little weirdness there. It shouldn't be there. Alright, so that's the lesson. This is a pretty tricky one, right? Not necessarily the conditions on differentiability. That's not bad at all. But what is a little bit tricky is how you make a piecewise function differentiable at the cutoff point. You'll always have two things going on. Continuity, and you'll sort of get that, if you will, by setting the two y values equal, or at least the two limits equal as you come in from the right and the left. Then you have a condition that sets the slopes equal, and that is literally by taking the derivative and setting the slopes equal. And then combining those two conditions will give you differentiability, a derivative that exists because there are no corners and there are no discontinuities. Let's stop there. This has been a pretty weighty lesson. Thank you very much for joining me. Until next time, remember, don't get into a staring contest with a llama, because they spit. Still looking for a catchphrase at the end? If you have any comments, let me know. Bye for now.